from International Neural Network Society. So today's talk is about bio-inspired intelligent computing for smart grid from Professor Ganesh Kumar Vinayagamurthy. So before getting to that, if we just talk a little bit, just to set the tone about the brain. So in the era of this large foundation models with the billions of parameters, which are progressing in their way, if we just talk about the human brain, actually it seems like it just run on 20 watts of the power. And roughly it is like same as any dim light bulb, but yet it is outsmart world's most powerful AI models. I believe that people mostly will be agree with this statement. So that is quite inspiring. So the next time if someone calls you a dim bulb, actually it's a compliment. I take it like this. So it is the most efficient learning systems. So understanding it will make AI scalable and sustainable. This is which I personally believe and I do my research also. So the goal is about brain like intelligence. And today we will hear about that kind of a brain inspired intelligence and efficiency, how it can shape the next generation of intelligent system from Professor Vinayaga Murthy. And a very quick introduction about him. He's distinguished professor in power engineering at Clemson, recipient of multiple awards, including the Young Investigator Award. He's IEEE Fellow and INNS Vice President for Industrial Relations. So, without taking much time, I would like to invite him, and please, floor is yours.
Thank you, Prakash. If you can stop sharing, I will share my slides.
Yeah.
All right. It should be shared now.
Yeah.
Great. Thank you for that kind introduction. And hello to everyone that has joined this webinar across the world. So in this webinar, I'm just, as Prakash had a nice introduction, we're going to basically look at bio-inspired intelligent computing technologies, which I will illustrate for smart grid. So here's an outline for my presentation. I'll give a brief introduction, and then I will go into intelligent computing. I'll try to get across the message that intelligent computing is beyond AI. And I'll focus on specifically brain-inspired intelligent computing, short form BIG. Then I will, go into big applications in smart grid. Then I will get into scalable and sustainable AI, which will be cellular computational networks. And I will have a couple of examples to illustrate that. So complex systems, as we all know, are made up of many components, like the brain as we see here in the video. Those are basically neurons. And these neurons basically go into burst behavior, which is basically distinct behavior or properties of the brain. There's nonlinearity, there's emergent behavior, like the burst. When the brain undergoes learning, such things happen in the brain. And this is clearly a nonlinear system, a complex system that's nonlinear, there's spontaneous order of reactions and actions and reactions, and lots of adaptations, right? And other examples of complex systems are basically, the air transportation network. We can mention quite a few. The electric power grid, what we see there in the slide, is the subtransmission and transmission network of the continental United States. Such systems are very difficult to model due to the dependencies, the relationship that exist, the interaction between the different parts of the system, between the system and the environment. Yeah. So models are very important. And I say here, models are the heart and lungs of advanced analytics and intelligence. It's a science and art to develop such models. Today we have a lot of IoTs, lots of sensors and actuators, lots of data that we can get from complex systems. But it is important that this data be turned into information, information into knowledge, and knowledge into understanding. So the models that we're talking about are models for complex systems that are accurate to the time instant, current time instant. Yeah. So we call this the real time wealth of knowledge. We say wealth of knowledge because these models are rich in dynamics. They capture the richness, the complexities that exist in this complex system. So it is a wealth of knowledge, richness in the dynamics. Having such models, we can basically have three strands of thinking: sense making, decision making, and adaptation, which is what we call as the computational systems thinking machine, CSTM. Then we can basically use this kind of models to make sense of the data, turn that data into knowledge and understanding. Using that knowledge and understanding, we can make decisions, and not every decision can be implemented on physical complex systems. So there has to be some adaptations of these decisions. So we can use digital twins for the CSTMs. Digital twins basically, it's a virtual model of the physical complex system that we're talking about here. And this digital twins basically can replicate the complex dynamics of such systems. And it allows us to better understand and operate and manage such systems. So digital twins are key to intelligent operations and management of such complex systems, including the power grid. And even digital twins of the brain, for us to understand the brain better. Today, digital twins come alive because of the number of IoTs that we have, small to large, that more than 50 billion IoTs today in the world, right? And of course, the computational power that we have, and of course, the AI methods. So AI and digital twins can basically change the way we study complex systems, such as the power system. So we have lots of IoTs that we can deploy on a complex system. We can get the data, and then using the data, we can use AI methods to basically build digital twins. So intelligent computing will be essential to maintain the quality of these digital twins. You're talking about the power grid for grid operations and management, while mitigating the climate effects of energy consumption. One thing we want to know for certain is that we do not want to deploy a lot of models that are consuming energy. The kind of methods we use should not be reversing what we are trying to achieve. Yeah, it should not be in the backward direction. So sustainable and AI would be key to that. So some of the approaches that we can look at are computational intelligence methods, okay, for implementing some of this AI. And computational intelligence methods basically are models and tools of intelligence that can just take this data from these IoTs, process them using some representational mechanisms such as parallelism and pipelining to generate just-in-time responses that are highly fault-tolerant, robust, intelligent models. Yeah. And some of the soft paradigms are basically neural networks, fuzzy systems, evolutionary computing, artificial immune systems, swarm intelligence. And then, of course, we can form hybrids of these techniques. But today's AI, the neural networks are the brain of today's AI. AI has now come alive. And what's the engine behind the AI? It's basically neural networks inspired by the brain, right? And there are all kinds of different neural networks. It's a simple neural network as shown here in my slide with just three layers: an input layer, a hidden layer with one neuron, and an output layer with one neuron. Basically, if you only have four parameters as shown in this kind of small neural network, W11, W12, V11, V12. So during the learning process, the input and output data that you have that you use for learning, you're basically learning these four parameters, which are known as the synaptic weights. Once a neural network is trained, then you can replace that neural network with a mathematical equation. At this point in time, basically, it is no longer a black box. The communities, some of the community basically views neural networks as a black box. But once a neural network is trained, it's no longer a black box because we know the mathematical equation that governs the input-output relationship. If it's a dynamic system, this relationship will be changing. And then, of course, the online training will identify this synaptic weights to represent the dynamics at that point in time. Of course, today we use deep neural networks, right, with millions of neurons and several more millions of parameters, right, for the connectivity, and several hidden layers, so that the way it's different from a multi-layer perceptron is multiple hidden layers. And if you want to train such large neural network that require millions of synaptic parameters to be identified, the data that is needed will be tremendous. And of course, when you have a lot of data, then the training time is huge. And when the training time, for some of the applications we have today, some of this could be weeks long, 6 weeks, 7 weeks, running on high performance computing that consumes 10 megawatts. Yeah. So basically, when we look at deep neural networks, lots of data are needed, lots of training time, and of course, a huge amount of energy being consumed, right? And this is the amount of energy consumed by some of these deep neural networks could be more than the energy consumed of the entire city of New York, right? So basically, we can say that the deep neural networks are energy-hungry beasts. And this is something for us to think about. Do we want to run large neural networks that are consuming AI that consumes huge amount of energy? This is not sustainable. So this takes me to intelligent computing. So in today's AI using deep neural network also faces other major challenges: interpretability, generality, scalability, sustainability, and autonomy, right? And most of the current AI technologies fall short compared to brain-like intelligence. And they only work on specific areas of task. So we're basically diverging from what brain-like intelligence is. So I like to draw us back to some basic elements of intelligent computing. And these are basically brain-like intelligence, machine capabilities, and also the physical world composed of all things. Yeah? So the integration of all of this and how we solve whatever problem you're trying to solve requires intelligent computing. Today, computing machines can mimic problem solving and decision-making capabilities of brain-like intelligence. But intelligent computing is beyond that. It is intelligence-oriented and intelligence-driven. In a nutshell, we can say that intelligent computing is basically intelligence for computing, which is meta-intelligence, plus computational intelligence, which is general intelligence. So today we have AI, which is the second part of the right-hand side of the equation. And intelligence for computing is what is needed to where we can then use the AI methods to basically have intelligent computing. And some of the applications that I'm going to show you today in Smart Grid basically is around this concept of intelligent computing. And we are only using computational intelligence to solve the problems, but we have to first figure out, we have to deploy intelligence to figure out the computing architecture. So with this, I will take us back to spiking neural networks. Okay, spiking neural networks is basically the type of, now the most closest neural networks to what the brain uses, yeah? So spiking neural networks, short form SNN, try to capture the power of living brains to operate on massive amounts of information and do so efficiently. Spiking neural networks in the brain are highly parallel and distributed architectures. We know today lots of work exists on showing that spiking neural networks are excellent at pattern recognition. But however, it is still challenging to apply spiking neural networks to nonlinear control problems, such as the power grid. Basically, for the reasons of converting continuous values to spikes and then showing that this spike contains the information, how do we embed information in the spikes, and that it is reversible, right? And one way to think about deploying these spiking neurons is to say the activation function is basically a spiking neuron, yeah? And we can use the spike rate and the interspike interval as a way of converting from continuous to spikes and vice versa. So here we have an architecture developed in my group on a biologically inspired spiking neural network, where we take a continuous input, we use an encoder to change it into spikes, and then we have a spiking neural network, and that basically the input outputs are spike, and then we have a decoder that interfaces with the world, with the physical system in analog form. So how do we create this encoder? Basically, the encoder's task is to take continuous values of numerical inputs and generate a spike stream. And of course, the spikes, as I mentioned, must contain the relevant data, the information eventually that leads to the knowledge and understanding. Otherwise, it's garbage in, garbage out. And of course, we must also be able to prove that when we reverse the spikes, we get back our input data. So reversibility should be a test for this encoder. There are lots of methods in literature. We can use the Poisson rate encoding method, the Gaussian receptor fields, the dual neuron n-bit representation. Today, I will show you the last two methods for encoding, right? So if we look at the Gaussian receptor field, basically we use a number of Gaussian functions as shown on the slide, on the image on the top right. And basically, if we want to encode some continuous values P and Q, then we can basically we can determine which of these neurons, basically the neurons are here, the Gaussian, we can see the one that basically has the highest activation is the neuron that gets fired. And you can see the ones that have the lowest activations are the ones, the neurons that have the highest activations are the ones that get fired early. And the ones that have the lowest activations are the ones that get fired later. So the firing delay is basically how we encode this. And then here, basically, I'm showing you both the Gaussian receptor fields method for encoding as well as the dual neuron n-bit representation. Here we have an input with multiple frequencies embedded into it and in a sine wave. And here we can see the encoded spike train with the GRF method. And then, of course, with the dual n-bit representation, again, there we use two neurons, one for the, when there's firing is a 1, and then no firing is a 0. And you can see quite nicely these methods encode an analog signal like the ones you would get from power system, voltage and current waveforms, convert them into spike trains. Then the next part of it is the engine, which is the spiking neural network. So here we use the polychronous spiking network, exploiting the polychrony that exists. And we can create that by basically, because of the timing, the synaptic delays, we use the Escovich's model here to form these polychronous circuits, right? Even just with a 5 neuron, we can see 14 distinct polychronous groups. When we increase that neurons to 6, you can see that the polychronous group, it goes up to from 14 to 37, only with 30 synapses. And what the equations we see here is for the Escovich model of the spiking neuron. Yeah? Herein, basically, of course, once you set up the spiking neural network, then you basically use spike time-dependent plasticity basically to mature the spiking neural network. And what we see here is on the top, we see 100 neurons. And when the maturation happens, you can see how the neurons weights basically separate. And when you have 1,000 neuron pairs, and even though it doesn't look like there's a separation, the graphs on the right show that the neurons basically separate out during the maturation process using the SDDP running and basically reinforcing the neurons that are firing and inhibiting the ones that are less firing. And you can see they settle. So basically, we can mature the spiking neural network engine. And then the third part of this development is the decoder, right? And the decoder is basically to translate the spike outputs into continuous values so that we can use it in control of power systems or some physical system, dynamical systems. The two-step process here is to convert each of the neuron spike streams into a numerical output and then basically have an algorithm to extract a desired dynamics. So we use a watch window here with some Gaussian functions basically, and then we have an MLP, a multi-layer perceptron, to basically aggregate these numerical values, and then we get basically a final output. So this is the architecture we have put together, and now in this slide, I show you that it works for learning this multimodular sine wave. We, of course, start off with online training, and initially the first stop shows us with the spikes, and then eventually learning the target. As basically as it continues, you can see the curve is the spike train is following the red curve. Eventually, as more iterations takes place, it tracks the time series, and thereafter testing demonstrates that the spiking neural network has learned this time series. We take this to power systems. On the IEEE 68 bus system, we basically apply it to learn generator dynamics. The IEEE 68 bus system is a New York, New England benchmark power system that we use in power system studies. And here we're just demonstrating it for the two different areas, one learning generator 10 dynamics and the other one learning generator 7 dynamics in different areas. And we compare the performance with a standard multi-layer feed-forward network and a spiking neural network. On the left, you see the multi-layer perceptron, and on the right, you see the spiking neural network. And clearly, you can see the percentage errors. The spiking neural network is able to do better than the multi-layer perceptron. So we show that the spiking neural network, by doing our proper encoding and decoding and working with the spike trains, is able to learn the dynamics of a complex system. Here we show natural disturbance like a short circuit or a disturbance that could happen on a power system. Again, we can see the errors are much smaller with the spiking neural network compared to the multi-layer perceptron. So now I'll move forward into more control methods. What I showed you is modeling. Yeah. So we can now learn like the brain does learning to do control on optimization. And this is a method, adaptive critics is a method that replicates how the brain handles a large number of variables. And of course, the concepts of adaptive critics are basically synthesized from the combined concepts of ADP, approximate dynamic programming, reinforcement learning, and the using of neural networks to get real-time derivatives by using backpropagation. Of course, this has been applied to solving dynamic optimization and optimal control problems. Basically, the architecture of an adaptive critics design consists of two networks, the actor and the critic. And of course, they can be model dependent or model independent. For complex systems, we want them to be model dependent. So the actor can basically serve as a controller, a dynamic optimizer, or even a scheduler. Yeah. So basically, the critic approximates the Bellman's equation of dynamic programming. It's a forward-looking network, and it basically tells how good or how bad the control or the optimization solution is, right? And the nice thing about the critic in this ACD architecture is that the critic is a self-learning network. So this is exactly how human brains work. Human brains basically self-learn. And we mimic that by basically using two versions of the critic over time, one at t and one at t minus delta t, to basically have the critic learn. The critic is a supervised, a forward-learning network that learns the Bellman's equation of dynamic programming, J, the Costigo function, And using the cost to go function, you're basically able to get the derivatives to train the actor. So we apply this method to this IEEE 68 bus system to solve a challenging control problem here. Basically, is to damp out oscillations that exist in the system. Power oscillations. This is a known problem when you have two large areas and there's power transfer. In this case, it's New York, New England. New York purchases like 1500 megawatt of power from New England. And if there's a disturbance on any of these major transmission corridors shown here in red, then there'll be oscillations in some of the lines. These oscillations, if not mitigated, can lead to blackouts. So basically what we do is we design a controller K. An idea is to design this controller, a nonlinear controller. It's basically a power oscillation damping controller. We're going to exploit a fax device known as therristor controlled series capacitor to basically damp those oscillations. So we'll do some series compensation to get rid of this oscillation. The question is, how do you design this controller K? There are multiple ways to do that. We can follow classical control methods like state feedback, or we can use H infinity, LMI-based linear matrix inequality-based H infinity control method. But in this case, we basically introduce a data-driven approach, the adaptive critics. And we compare with the advanced control methods, the H infinity and the state feedback. So this is the adaptive critics design, which is the HDP approach with the critic. We develop the model. The model is basically using a neural network to identify the dynamics, as I showed you with the spiking neural network. Here we show some test results to demonstrate the different controller responses. And you can see we have the state feedback, SF, the H infinity, and then the adaptive critics, the heuristic dynamic programming method. And you can see for a disturbance, a critical line to ground fault for 5 cycles and cleared by opening a line, you can see that the adaptive critics, the black line, has the quickest damping of this oscillation. The time response results also shows that, and also the frequency response results as well. This study was done in collaboration with the Imperial College Control Group to basically compare H infinity and the classical methods with the intelligent control methods. The other problem where you could really become rich if you're able to solve this, where every utility would want you, is the dynamic stochastic optimal control, right? So this is today optimal power flow. It's a challenging problem as the system gets larger and with lots more integration of renewables. The way this is done today is using basically 3 different control layers. So you have the tertiary control layer where steady state OPF is done every few minutes, 5 minutes, 10 minutes. In the secondary control, we have the automatic generation control and the regional voltage control. At this point in time, the active power and the reactive power controls basically are separated. At the tertiary level, they're combined. Then the primary level is even more separated. We have the speed governor and the excitation controllers and the fax devices. So this basically goes from nonlinear at the tertiary level to linear at the secondary and primary level. So what we proposed here is to combine the automatic generation control and the regional voltage control into one dynamic OPF, dynamic stochastic OPF, which will do the controls every second, 2 seconds based data driven using this brain-like adaptive critics techniques. Of course, I already mentioned adaptive critics basically solves optimal control problem, and this ACOPF is an optimal control problem. So we basically apply this using a more advanced adaptive critics method known as the dual heuristic dynamic programming. Instead of approximating the critic approximating the cost to go function, the critic basically approximates the derivatives of the cost to go function, and it makes it more robust for uncertainties in the system. Using the synchrophasor data, which we have on the power system, we are now able to pull data, and we can now implement this control 1 to 2 seconds, basically providing deltas to the treasury control. So now, if the treasury control is done every 5 minutes, we can correct that in system dynamics changes every second to 2 seconds. And then basically we can embed in the control objectives so many different sub-objectives, like minimize the operation cost, maintain the frequency, minimize the frequency deviation, minimize the voltage deviations, ensure the line loadings are within the limits of the lines, minimize losses, make sure that the generators are loaded within the acceptable range. Also minimize the control efforts. We don't want to work so much, the controllers to work so much that we basically wear them out. Yeah. So we also want to minimize. And at the end of the day, we want to maximize efficiency, stability, and security. So it's, again, going back to the properties of brain-like intelligence handling multiple things at the same time. So we can bring all this into sub-utilities. In adaptive critics literature, we use the concept of utility. The same thing used by the computer science people is known as the reward function. So here we basically have all this put into the utility function, area control area, voltage profile, line loading, fuel cost, and so forth, and we weight them. Yeah, and there's some results to show you. The red lines are basically the brain-like control, showing that the frequency can be better regulated when a load trips, and the tie line flow, the inter-area power transfer can be quickly restored with brain-like control. When a line trips, the brain-like control can ensure that there's no further cascaded outages. The decisions are looking ahead. When there is a huge variability in the load or renewable energy, the frequency with this kind of control can be better maintained, as we can see with the red line. With a huge variation, the 60 hertz can still be maintained. So these are some of the advantages. So what I showed you here is on a small system. The idea is, how do we scale up? And now we take this to the 68-bus system. Again, in this case, we have multiple intelligent controllers interacting with each other. It's a 5-area system. We have area 1 controller, area 2, area 5, area 4. And then we have a global DSO here. So we now establish a hierarchy of intelligent controls where intelligent controllers are interacting with each other, and how this is again done using the DHP approach. And the results on the right basically shows that when there's wind fluctuations and all kinds of disturbance on the grid, the frequency can be better maintained when we have this area controllers and global controllers compared to the traditional control. So better power control, better objectives can be achieved, right? So the idea is now, how do we scale up our brain-like intelligence? Yeah. So we basically need distributed architecture, distributed CSTM. As I showed you in the previous example, we have numerous intelligent controllers, but again, these are still handful. How about if we have a system that's going to require millions? How do we ensure that they are in harmony, they're coordinated, and there's proper communication and exchange of information? So this takes me to the next thing that I want to share with you is the cellular computation. Cellular computational networks are basically inspired by basically building blocks, such as Lego pieces, like a pile of Lego. When you look at this pile, you see these Lego pieces are basically different colors, different shapes, right, different sizes. And when you have this kind of building blocks, of course, Lego comes from Denmark, basically. It simply means play well, right, in Danish, right? And it's left to your imagination what you want to build with Lego, yeah? So you can build any kind of, for someone who is a novice, you can basically build a structure like that. Eventually, when you play well, and you can build more creative, innovative architectures with Lego. You can build the Titanic, the Taj Mahal, the Colosseum, right? So how about building intelligent machines using the concept of Lego, building blocks? So this takes me to the CCM. The CCM basically is made up of cells, okay? And the cells basically are computational units. They basically have, that's the prime unit, you have the learning unit, and then the communication unit. That's a generic cell. Then you can put the cells together in whatever topology, This is just one topology that I'm showing, but it can mirror the topology of the physical system. You can basically take the physical system and decompose it into subsystems. And the subsystems basically can be also decomposed to mimic, to basically model the components that sit inside. So you can basically take the cell all the way up to the component level and have a hierarchy. And what you see in the CCN is, if you look at this topology, the output of any of this cell, if you see the cells basically can have a neural network or can have some kind of computational algorithm. It could be a time series. But when you look at the output as a function of the inputs, and then basically every cell has a first order inputs and maybe a second order and a third order. When you unfold that, you basically see for an N cell CCN, there's N deep neural networks. But the beauty of the CCN is that each of the cells are basically built as needed. They're basically brought in as needed. So let me illustrate a little more on the CCN. If you take a system with 4 inputs and 4 outputs, and you want to model this, you can just say, oh, I'm going to use an MLP to do that. And when you use an MLP, basically, it is static. Okay. So if the system is static, the MLP will be perfectly fine. But if the system is dynamic, then you say, oh, I'll use a recurrent neural network. But when the number of inputs increases from 4 to 1,000,000, and the number of outputs increases from 4 to 1,000,000, then the recurrent neural network will have 1,000,000 inputs and 1,000,000 outputs, and then it becomes a deep neural network. And we know the curse of the deep neural network, right? So now with the CCN, you only model the connectivity between the nodes, and basically it is a recurrent neural network with sparse connections. Okay, so you have cut out a lot of neuron synaptic weights, and it's very sparse. Okay, and if you take the other advantage of the CCN is the ability to basically allow asynchronous learning. When the performance of a cell degrades, you only need to trigger the learning in that particular cell, not the entire network. Again, this saves a lot of energy. So there's sparsity in the learning itself. So you save a lot of amount of energy. And also the other nice thing about the CCN is that for the power system, for example, if a disturbance happens at cell 1, that disturbance will only propagate at the next time instant to cell 2, as we see it given by this topology. And then following time step, it will propagate to 3 and 4. So therefore, it also provides how it mimics exactly how electrical signals propagate in the power system. And the same thing in any dynamical system that are connected in a network, in a complex network, same way. So basically, this is, again, each of the cells can be, you can add more cells or you can delete cells, right? So it is easy to maintain and retune a CCN compared to a deep neural network. So in this slide, I'm going to take you to the 68-bus system again, modeling that using the CCN architecture, again, trying to model the generators. And I want to show you here that it is able to capture the dynamics of the 68-bus system, electromechanical oscillations. But what I want to really point out is the number of parameters. With the CCN, we only need 514 parameters, whereas with the time lag recurrent neural network, we need 3,076. That's already a 6-order reduction in magnitude. And if you look at for the same amount of epochs of training, basically the error attained by the time lag recurrent neural network and CCN gets a lower. And if you use this performance index, you see that the performance is at least 6 times better. And this is on a 16 generator system, but if you take this to a largest network, this performance will increase. So here are some of the attributes of the CCN. It is cellular, it's modular. You can use asynchronous computing. It's easy and efficient in learning. It's distributed and parallel. It is highly scalable. And of course, when any of the cells are attacked, it is resilient, or for one or more reasons, the performance degradation will be graceful. Last but not least, it is a sustainable architecture meeting the UN Sustainable Development Goals. Right? So I could show you more examples of application of this CCN. This is another problem on the distribution system, distributed volt-var control. Again, we can model a complex system by making it into subsystems, and subsystems modeled by cells. And we can do different levels of optimization at the node level, at the component level, at the subsystem level, at the system level. So basically, any complex system, using the concept of divide and conquer, the CCN works pretty well to handle complexity. And some of these results basically shows that when we are able to do with the CCN, we are able to handle, this is a bottom-up approach, and it's much better to do it this way. And the complexity, the adaptability, or the stability, all of these are much better. Yeah. And this results basically shows the top curves basically without the CCN optimization, and the bottom curves with the CCN optimization. And the goal is to keep these voltages around 1 per unit. Okay. And the last application that I will show you here is cybersecurity. So cybersecurity is very important for complex systems such as the power system. And here we basically study the deployment of the CCN architecture for modeling the communication network, which is done by the synchrophaser here. And we basically create a virtual synchrophaser to overcome basically denial of service attacks. So for example, here we demonstrate how important that PMU7 is to the AGC, automatic generation control. So the PMU7 provides a feedback to this controller. If an attacker wants to attack the system, it is PMU7 that one would attack. And when that attacker probably will do that when there is a fault, so so that the system operator cannot distinguish whether it's a fault or an attack. And if you take that PMU7 out for a few packets of that data, then you can basically drive the system unstable, and this could basically lead to a blackout. Now we implement this virtual synchrophaser network using the CCN concept. So each of the cells basically is a virtual IoT, a virtual PMU. In this case now, when the cell 7 or the PMU7 is attacked, the CCN basically provides the frequency feedback. As you can see from the curve, the CCN has learned the frequency variation of the system. You cannot even distinguish the estimated value of the frequency from the actual value of the frequency from the PMU. And now, whether it is 300 packets or 600 packets, the CCN basically provides the frequency feedback, and we are able to see that it is only the fault that causes the oscillation, and the system restores. Even if there was an attack, that attack was seamless, did not have any effect on the system. And this is because we implemented distributed AI using the CCN architecture. So with that, I will summarize my presentation to allow some time for questions. So in this webinar, you've basically been introduced to the concept of intelligent computing. Intelligent computing is intelligence-oriented and intelligence-driven. And it is just beyond just AI. It is basically intelligence for computation, how you design the computational architecture, plus using the AI methods. The AI methods are not going to give you intelligent computing. They're just tools. How you design the framework for the computing is the key. And that's what intelligent computing is about. Designing the framework to implement the computing and then using AI tools. And I've presented to you the cellular computational network as a framework for scalable and sustainable computing to basically develop scalable AI, because we want tools that do not consume too much of energy. Deep neural networks is not the way forward, in my opinion. It is going to basically consume a lot of energy, and we're going to go backwards in terms of energy consumption. And not for power systems, there's AI for sustainability, and then there's sustainable AI that we have to look at. And CCN is a sustainable AI approach. And of course, I've illustrated these concepts of intelligent computing through the different architectures put together, and the tools of AI have been used to solve smart grid problems. With that, I'd like to thank you for your attention, and I'll be glad to take any questions that you may have or comments.
Thank you so much. Thank you so much, Professor. So yeah, now we can open the floor for the questions. So yeah, any participant can on there. I can unmute and can have questions.
Yeah.
Hello, I would like just to thank Professor Kumar Venayagamurthy for this successful webinar. I'm Carlo Morabito, and
Thank you.
Hi, Kumar.
Yes, hi, Carlo.
Thank you for your presentation. Very interesting indeed. So I hope to meet you again in the future. Kumar is the Vice President for Industry Relations of International United Society and also a candidate for the future presidency. So good luck, Kumar, and thank you.
Thank you. Thank you. I appreciate that, Carlo.
Okay. Yeah. So yeah, Abdullah, I guess you can ask your question.
Yes, thank you, Professor Kumar, for this presentation and for covering one of very important topic. It is the intelligent computing. So, in recent research, we see a lot of emphasis in machine learning, AI, deep learning, but we see a lot of missing piece within that, which is the how we can structure the intelligent computing actually to apply intelligence before we conduct the computing itself.
Yes.
My question is related to, as a part of AI stages is more of the applications of setting the data or pre-processing the data using principles, PCA and other techniques with data reductions of the complexity. Is that what you are proposing here as intelligent of computing could be classified as a part of pre-processing of the data before we actually integrate it to a deep learning or machine learning? So can we consider that as a part of pre-processing the data before we go to the learning process? Thank you.
Yeah, thank you, Abdullah, for your question. Yeah, of course, it's more than just the pre-processing of the data. It's actually, if you want to before a building can be built, you need to have the architecture and then the building, right? So this is like architecting the computing framework. So that is the first step. And I think if we can, the intelligent computing is more emphasis on the architecture for the computing. How are you going to, if you're dealing with complex systems, what is the best way, the robust, the resilient, the sustainable way to carry out the computing, right? So once we have that framework or that architecture, then we can deploy AI methods in the different parts of the architecture in a distributed hierarchical way, and that will be resilient, that will be sustainable, robust, all these features. But this architecture is the key to successfully implementing AI. Otherwise, it's just like you build a house or a building, and then the storm is there and it falls apart, right? So the same way, it is going to collapse. These AI methods, the way we are using AI is not going to be sustainable. It won't be sustainable. It has to be thought through. That's why I say meta intelligence is the first step before deploying AI. And this is called intelligent computing. I hope that's clear, Abdullah.
All right.
Yes, thank you.
maybe, yeah, I can take a couple of more questions. Yeah,
Sure,
please.
sure. I think Zen has a question. He raised his
Yep.
hand.
Yep. Hey, Professor Kumar Valiagumus, morning.
Good morning.
It's great to hear your talk here today. Kind of refresh a bit of my memory. I have a question about that digital twin picture. So you talk about simulate power system in a digital twin, and AI could interact with the data analytics and so on. From my personal working experience, my background working on computational intelligence RL, and I have an application on smart grid as well. So what I'm facing is this generation of the students are more in favor of using Python open source code, right? There are tons of open source code they can run there. However, they feel when they integrate or apply into the smart grid power system or all those models, they realize many of the models were built in MATLAB and Simulink. So what is your takeaway for the current generation that when they really want to apply new AI or cutting AI technology, they have the big model, the code is in Python library, while the previous engineering problems are most likely were built for decades in MATLAB and Simulink. So practically, should students all go to Python and reinvent the power system model in Python, or they wanted to translate all these new AI algorithm in MATLAB to run the previous model? So we're
Yeah.
facing kind of a practical issue when we train students. So what is your takeaway for this kind of programming tools, and of course digital twin platform as well?
Yeah. So I think, of course, this is every time something new comes and it's on a different platform, it's always challenging to interface to use that. And I would say, I think the easiest would be if we can figure out an interface between MATLAB and Python. And I think already that is there. In fact, I think you can do that. But how to make this seamless is, again, for the vendors, like MATLAB and Python. I think MATLAB might be able to say, okay, make it more interoperable, right, with other platforms. Yeah, so that will make it easier for adaptation of this new emerging technologies and code that is available in one particular platform. Yeah, so I think that will be otherwise, if you will have to do the effort of converting from one to the other, which is also not a wasted effort. I think when some one or two people or software people take that effort to do it, I think it serves the community, right? So it's a kind of put it on the open source and get acknowledgments for that. So I think that's something we all do as academics, and our students do that as well. Yeah. So I hope I answered your question. So
thank you very much. I look forward working with you on the IGCN organization for 2027 as well. It's great.
Thank you.
Thank you very much.
Thank you. I appreciate that. We'll need a lot of people to work on IGCN in 2027. It's going to be in Cape Town, South Africa, and I'm looking forward to that and having a lot of great papers at the meeting. Thank you.
So I guess we have more questions from Nikita. Yeah.
Yes, hi.
Hi.
I have a question about and nice to see you again.
Nice to see you too.
Yeah, I have a question about the high frequency application, because in the high frequency application, they work in the microsecond and something like this. And most of the application based on the neural network and artificial intelligence work on the, for example, second and something like this. Also, for example, current and voltage for this high frequency is really, really small. So some neural network faces the problem for identification parameter for the this type of application work on the high frequency. So how can we solve this and something like this? This is my question.
I'm not sure, Nikita, I understand your question. So you're saying for high frequency application, what's the question on the high frequency applications?
I mean, some neural network is faced the problem for the identify parameter in the very, very
Okay.
short time. Yeah,
Yeah, yeah.
it's my question.
Yes. So yeah. So basically, I don't think it doesn't matter, I think, whatever the frequency is. But I think it is, we have to still adhere to Shannon's sampling theorem, right? So we need, if at least Shannon's sampling theorem says that we need at least two or more greater than the maximum frequency in the signal. But I think, if we use much more, like 10 times, I think you will be able to. But the question is, as the frequency gets higher and higher, are we able to, so the platform to execute the neural network also must be high speed, right? So because we have to make sure that the computational time of the neural network is much less than the maximum frequency in the system that we are trying to identify.
Yeah, exactly.
So again, when we deal with high frequency systems, the computing platform has to be the very high end. It must solve the problem, the forward path of the neural network faster than the sampling, right? So I think that is where the key is. Otherwise, you won't be able to do it.
Right. Okay, thank you so much.
Yeah. So that is the key there. Yeah. Thank you, Nikita. Nice to see you.
Okay, so do we have more questions from participants?
I think on the chat there is a couple.
Okay, yeah.
Okay. I think it was just a thank you message.
Yeah. So maybe I can add my one question here, like
Sure.
because it's quite a new field to me. So I like how this CCN and spiking neural networks if we compare for like computational efficiency, one has to choose something over other. So that is one thing, and which is like more close to biological realism, according to you. Right? So that would be good insight to get.
Sure. So I think maybe might have been a little bit of maybe it didn't come across clear. The CCN is a framework. And as I said, in every cell, you basically have a computational unit, a learning unit, and then we have a communication unit. So that computational unit basically can be a spiking neural network, can be a recurrent neural network, can be an echo state network, can be a time series, can be a simple differential equation. So basically, you can put whatever is needed for that particular node, right?
Okay.
So we can basically
so these are like a building blocks actually. Then we can make out of it.
Yes.
Okay.
Yes. Yeah, absolutely. And so you can throw in spiking neural networks inside some of the cells, right? And you can basically. So the whole idea is that the brain is spatial and temporal. The CCN allows us to have the spatial and temporal framework. Okay, so that's one of how it resembles the brain. And then, of course, spiking neural networks are more close to how the neurons in the brain are. And then you can throw spiking neural networks inside these computational units.
Then would it be also then so useful with like in our group also people do work on neuromorphic computing and hardwares. So that could be like, how do you see that could be as an enabler for such hardware advancements as also?
Yeah. So the CCN framework could be used to say, okay, now you have a neuromorphic cell.
Yeah.
Okay. And then you basically have a network of these neuromorphic cells. And then you basically can build an intelligent machine. So you don't need to have large neuromorphic cells. They can be few neurons, right? And it's easier to basically build with fewer neurons than many neurons. If you want to basically have a neuromorphic hardware for CCN, for deep neural network, it's almost impossible to do that. But definitely you can do that for a few neurons, 15, 20 neurons, 50 neurons. Yeah.
Thank you so much. Yeah.
Sure, I appreciate it.
So do we have more questions from participants? Otherwise, I would like to thank you, Professor, again for insightful talk. I got to learn so many new things. So That's really appreciate. So once again, thank you so much for your talk and the time and the question answer also. Thank you.
Sure. Appreciate it. Thank you all.